remember we're talking about equilibrium reactions. So let's talk about the equilibrium constant. Now, let's write down the expression for the equilibrium constant. The expression for the equilibrium constant has the same form as the expression for Q. The expression for the equilibrium constant has the same form as the expression for Q, so we should now be able to write down the expression for this equilibrium constant. So let's write that.
And even including the exponents.
Yeah, including the exponents, absolutely. Now again, since we're dealing with a gas, there's a default equilibrium expression and an alternative. The default is to work with partial pressures. If you want to work with concentrations, you have to specify that that's K sub C. If we were working with aqueous species, then the default would be to work with concentrations, and that would just be called Q equilibrium, because that's the only one that, because then you would never work with pressures. Now this is called the equilibrium constant. This is how this is usually written in the book. But I usually get lazy and just call it K because it's the equilibrium constant, so I don't have to keep writing EQ. So this is the equilibrium constant. Now, something should seem puzzling here, which is that we have the same exact expression on both sides. Why would we need two different names if it's the same expression? There must be some difference between these, which we haven't put on the board yet. Well, here's the difference. Q is based on the actual concentrations. K is based on what the concentrations will be at equilibrium. That's why it's called the equilibrium constant. So to make this correct, I should include this. And if you can read my writing, this is a little EQ for equilibrium next to each of these as a subscript. So I'm putting a little EQ next to each of these to show that these are equilibrium concentrations. Q is calculated based on what the actual concentrations are right now. K is based on what the concentrations will be at equilibrium, and those are two different things. So we should do the same thing here. Unfortunately, I've already used up the subscripts, so it's a little hard to find where to put EQ, but maybe I'll just put it over here to show that each of these are what the partial pressures will be at equilibrium, whereas Q is based on what the actual pressures are right now.
So you use Q to find the value of anything that's not at equilibrium.
Yeah, Q applies to situations when we're not at equilibrium, although Q could also be used at equilibrium. Q is based on whatever the actual concentrations are now, whether in or out of equilibrium, whereas K is based on what the concentrations will be at equilibrium. So K is only based on the actual concentrations if we're already at equilibrium. Now, usually in the book, they leave out the little EQs. Usually in the book, they would write K the way I had it on the board a second ago, because they just know in the back of their head those are equilibrium concentrations. But I think it's much better for a beginning student to specify that this is EQ, because otherwise you can't say the difference between K and Q. In fact, a lot of students don't even realize there is a difference between Q and K, or some students don't even know about Q, which is a problem, because it's important. So we have to distinguish between these two things. So we're going to keep putting in the EQs if I can remember to do that for the Ks. Now, let's suppose that the equilibrium concentration of the product is small. Does that mean that the equilibrium lies far forward or far reverse?
That the equilibrium constant is small? Yeah. Or is
lies in reverse.
Yeah, all right. What you said was right, but it wasn't quite the question I was asking quite yet. So I was asking, what does this tell us about the equilibrium? Does the equilibrium lie far forward or far reverse? Well, it tells us that in equilibrium, we won't have much products. If we don't have much products in equilibrium, that means that the reaction hasn't moved very far forward. So the equilibrium lies far in the reverse direction. And if the equilibrium product is big, what does that tell us about where the equilibrium lies? Yeah, far forward. Now let's talk about what you were just bringing up a second ago. What does this tell us about K? If there's only a small amount of product in equilibrium, would that be a case where K is big or small?
Small.
Yeah, because if product is small, this numerator would be small, which would mean K is small. And when the equilibrium, when there's a lot of product in the equilibrium, K is big. That's right. What this tells us then is the larger K is, the farther forward the equilibrium lies. K tells us how far forward the equilibrium lies. K tells us how far forward the equilibrium lies. Remember that we're not looking at a reaction that goes to completion here. We're looking at a reaction that goes to equilibrium, so it's going to go for a while and then stop. That is, the net reaction is going to stop. Eventually the net reaction will stop. Well, this tells us how far we go before the net reaction stops. If K is small, we're only going to go a short distance before the net reaction stops. But if K is big, the reaction is going to go far forward before it stops. In the extreme case, if the reaction did go to completion, then K would be near infinity. And we would approximate that as saying going to completion. And what if K was 0? If K was 0, then there would basically be no reaction. The reaction hardly gets off the ground at all. Sometimes there really is hardly any reaction at all, and then K would be 0 or close to 0. But in most practical cases, K will just be a finite number. And if it's a big number, then the equilibrium lies far forward. And if it's a small number, the equilibrium lies not very far forward. So now we can see the relationship between Q and K. Q tells us how far forward we've already gone, and K tells us how far forward we will go when we get to equilibrium. Q is based on how far forward we've gone actually, and K is based on how far forward the equilibrium is. Or to put it in colloquial terms, Q is where we're at, and K is where we're going. People tend to have a poor intuition for this, so I think those are a really useful motto to have. Q is where you're at, K is where you're going. K does not tell you where you're at. It tells you where you're going. Q tells you where you're at. So K is the destination, and Q is where we've gotten so far.
The you are here.
That's right. Even better. K is the destination, and Q is the you are here. That's right.